In the previous section, we talked about linear transformations. And one of their important ideas or features is that they can be represented through matrix multiplication. More specifically, if you dream up any linear transformation at all, if you can show that it's linear, then there's some matrix out there that by using that matrix to multiply onto other vectors, you can accomplish the same effect as your transformation. So that's just the informal idea, but let's go through this more carefully. So we're going to start by introducing some notation and a new term called the standard basis vectors. So here's how it works. Start with a positive integer n, and you can consider Rn, the set of all n-dimensional vectors. Well, there's a specific list of vectors, of n vectors, e1, e2, all the way up to en, that have certain definitions. So these symbols, e1, e2, all the way up to en, denote these vectors. e1, just put a 1 in the very first coordinate and then put zeros elsewhere. So I'm just going to say 0, 0, dot, 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 0 to indicate the rest of the coordinates are 0. And then the second coordinate, the second standard basis vector, e2, is going to have a 1 in its second coordinate and zeros everywhere else. So you see the idea. The index just tells you where to put the 1, and all other coordinates are 0. So here I've got a 1 as an index, so the first coordinate is equal to 1. Here I've got a 2 for the subscript, the index, so that means the second coordinate is equal to 1 and everything else is 0. Right, so the next one, if I went E3, I would say 0, 0, 1, and then zeros everywhere else if I continue on in this pattern, right? But I'd keep going all the way till the very final vector in the list, En, and that has a 1 in the nth coordinate and zeros everywhere else. Okay, so those are the standard basis vectors, and they're quite useful. Really, they're the building blocks of all other vectors. You can build all other vectors by using these standard basis vectors and then building the appropriate linear combination. Let me show you. Let's clarify in case there's anything that's not clear. Let's write down a specific example. Let's talk about R3. So in R3, E1 is 1, 0, 0. And E2 is 0, 1, 0. And then E3 is 0, 0, 1. Okay, so if you're talking about R4, well, then your standard basis vectors would be 4-dimensional vectors, and you'd have 4 of them. Okay, so let's talk about the standard matrix now. If you start with a linear transformation, so let's start with that. We've got a linear transformation T. Let's say it goes from Rn to Rm. So its standard matrix is going to be an m by n matrix A. So that's how the next part of this definition. So it's the standard matrix of your transformation T is going to be an m by n matrix, and it's going to have the following property. It's got to satisfy this statement. So what does this mean here? Well, the first part just says T of x is equal to A multiplied by x. Remember what I said a few moments ago when we started? The idea is that the standard matrix of a linear transformation, it's a matrix that can accomplish the same job as the transformation does through multiplication. So here on the right-hand side of the equation, you're taking an unknown vector x and you're multiplying it by the matrix A. So that's going to give you some result. Here, you're taking the vector x and you're plugging it into the linear transformation as an input vector. So this property is saying that those two things have to be the same. Now, this is not just some equation involving an unknown value x. This is something that has to be true for every possible input vector x. Okay, so what you're really saying is that the standard matrix, you're saying that the matrix A is essentially equivalent to the transformation. The transformation doesn't do anything that the matrix can't do just by using multiplication. Okay, well that's what a standard matrix is, but how do you find it? Right? We did a couple of examples in the previous section where we worked them out kind of using fundamental principles, and that method works, but it becomes less practical as you get into higher dimensions where your input and output vectors have more and more coordinates. So there's a straightforward method that you can use the standard basis vectors. If you have the transformation T and you want to find its standard basis vectors, if you have a transformation T and you want to find its standard matrix, so you want to find this matrix A, Just plug each of the standard basis vectors into your transformation T. So we'll go T of E1, for example. Then we're going to go T of E2. And then we're going to keep on going, and we're going to work out all of these all the way up to T of En. And then what you're going to do is you're going to just put those together. Paste those together into a matrix. So they're columns. I'm just highlighting that fact, but you're going to put them together into a matrix, and that's what these square brackets are meant to indicate. Let me actually add this up. This is going to be equal to the matrix A from this definition. That's the matrix A that you want. That's the standard matrix of T. Okay, so let's put a box around this because this is a really, really important formula. This is kind of like a formula. Essentially, it is. Let's look at an example. So we've got a linear transformation T. It goes from R3 to R2. Okay, so its input vector has to have 3 coordinates, and its output vector has to have 2 coordinates, and is going to be determined by this formula here. Okay, and we're asked to find its standard matrix. So the previous formula here that we just wrote down says that all we have to do is plug in the 3 standard basis vectors in R3 to our function T. So T of E1, let's start with that. That's just T of 1, 0, 0. So how do we work out T of 1, 0, 0? Just plug in a 1 for x1 and plug in zeros for x2 and x3. And whatever you get over here is going to be the output value. So that's just going to give you 1, 0. Okay, and then T of E2, that's going to be T of 0, 1, 0. So you're plugging in a 0 for x1 and x3, and you're plugging in a 1 for x2. So what's that going to give you? Well, for the first coordinate, you're just going to have 0 plus 2 minus 0. So you're going to have a 2 for the first coordinate, and then you're going to have a 0 for the second coordinate, because x1 and x3 are both going to be evaluated at 0. Okay, and then T of E3 is going to be T of 0, 0, 1. So plug in a 1 for x3 and a 0 for x1 and x2. So what is that going to give you? Well, the first coordinate, this is going to give you -1, and these are going to both be 0. And then for the second coordinate, this is going to be -2, and this is going to be 0. So you're going to have -1, -2, like that. Okay, so that's all the pieces that you need. So now the standard matrix is given by A. Let's write A is, and then we'll just write out the formula to remind yourself. It's going to be T of E1 for the first column, T of E2 for the second column, and then T of E3 for the third column. So let's put that together. We're going to get 1, 0, 2, 0, -1, -2. Okay, so that is our standard matrix. And the dimensions are what we expect, right? If you go back up to this definition, if your transformation goes from Rn to Rm, the dimensions of the standard matrix should be m by n. So in other words, the dimension of your codomain by the dimension of your domain. So we went from R3 to R2, so we're expecting to have a 2 by 3 matrix. And that's exactly what we had, right? 2 rows and 3 columns. Okay, the next example here says to find the standard matrix of what? Well, of a linear transformation okay, well, we're given a header. It goes from R2 to R2, but we're not given a formula for it. We're just told in ordinary language what it does. So what does it do? The linear transformation T, I don't think that probably doesn't help. I'll stop circling things like that. So it doubles the first coordinate and triples the second. So if you plug in a vector, it's going to take the first coordinate of that vector and multiply it by 2. And then it's going to take the second coordinate of that vector that you plugged in and multiply it by 3. So what's the standard matrix? Well, it's easier to answer that question if we first just say, okay, well, what do we need? If you need to find the standard matrix, you need to know what T does to each of the standard basis vectors. So let's start by working out T of E1, and then we can work out T of E2. So T of E1, in this case, we're talking about R2, right? So E1 is going to have 2 coordinates, 1 and 0. And, well, what is it going to do? It's going to double the first coordinate and triple the second coordinate. Well, the first coordinate's 1, so if you double 1, you get 2. And the second coordinate is 0. So if you triple 0, you don't change it at all. You just get 0 again. Okay. Then let's do the same thing for E2. So we got t of E2. If we double the first coordinate, you're just going to double the 0 and get 0. And if you triple the second coordinate, that's a 1. So multiply it by 3 and you get 3. So now you know what t does to each of the standard basis vectors. So it's a straightforward matter to put them together to get the standard matrix. So our standard matrix is going to be the matrix whose columns are t of E1 and t of E2. So put those two columns together and you're going to get this 2 by 2 matrix. All right, so there you go. That's the standard matrix of that linear transformation. So now if you wanted to use that, you could now come up with a formula that would give you the linear transformation T. But you don't need to be given a formula. If it's explained precisely what the linear transformation does, you can just use that explanation to figure out what the transformation does to each of the standard basis vectors, then put them together like we did here and get your standard matrix.